What happens when the darkest objects in the universe collide and sing? Not with light, not with sound, but with ripples in space and time itself. In late 2024, two black hole mergers were detected, just a month apart. Each sent out a gravitational wave that rang across the universe, clean, powerful, and eerily beautiful. But what makes these events truly remarkable isn't just that we heard them. It's what they revealed. Black holes that spin faster than ever recorded. A black hole that spins backwards, against the orbit it followed. These events gave us something rare, a laboratory in the sky to test the limits of Einstein's most famous theory, General Relativity. But what if the theory begins to crack? What if we are hearing something new, a whisper in the waves, telling us that Einstein's universe might not be the full story? In October 2024, the LIGO Virgo Cagra network of gravitational wave observatories captured a signal named GW241011. Two black holes, one about 20 times the mass of our Sun, the other around 6, spiraled into each other and vanished in a violent embrace. But the data revealed a surprise. The larger black hole wasn't just spinning, it was spinning rapidly, possibly one of the fastest spinning black holes ever recorded. Then, exactly 1 month later, another wave came through. GW241110, two black holes, heavier this time, 17 and 8 solar masses, merging more than 2 billion light-years away. Again, a twist. The larger black hole wasn't aligned with its orbit. It was spinning opposite to the direction of its orbital motion. This is incredibly rare and had never been clearly observed before. These were not ordinary collisions. They were clean, high-quality signals. And that meant something powerful. We could now test Einstein's equations in the most extreme conditions nature has to offer. Two events, 1 month apart, both whispering the same question into the fabric of space-time. Is this still Einstein's universe? In 1915, Albert Einstein changed the way we see gravity. No longer a force pulling objects together, but the very fabric of space and time, bending and stretching under the weight of mass and energy. This was general relativity, a theory so elegant it predicted black holes before we ever saw one. A theory so powerful it guided the GPS in your phone and explained the expansion of the universe. And yet, Einstein himself knew it was incomplete. His theory breaks down at the singularity of a black hole. It doesn't play well with quantum physics. So scientists have spent decades testing it, pushing it, looking for cracks. But here's the problem. General relativity always passes. Whether it's light bending around the sun or the ticking of atomic clocks on satellites, it always comes out right. Until, perhaps, now. With black holes spinning faster than anything we've ever measured, with spins tilted and reversed, with signals so clean they capture the echo, the overtone, of a black hole's dying ring, we are now testing general relativity where it should struggle the most, in the chaos of a black hole merger. Not in a laboratory, not on Earth, but in the universe's own proving ground. And what we're finding is both reassuring and deeply unsettling. Let's look at the signals. GW241011, GW241110. They weren't just powerful. They were clean, noisy, yes, but with clear patterns, like the tone of a bell or the echo of a drum struck in space-time. And from these patterns, scientists pulled out secrets. First, spin. The larger black hole in GW241011 was rotating at extreme speed, near the theoretical maximum allowed by Einstein's equations. In fact, had it spun much faster, the equations would have broken, space-time would tear, and physics as we know it would no longer apply. Then, tilt and reversal. In GW241110, the big black hole wasn't just misaligned, it was spinning opposite to its orbital motion. Imagine two figure skaters spinning toward each other, and one is spinning backwards. That changes everything about the collision. It alters the energy. It warps the gravitational wave. And yet, Einstein's theory still fit. Finally, overtones. Like a bell that doesn't ring just one note, but a whole chord. The signal from GW241011 carried multiple frequencies. These overtones weren't expected to be this clear, but they were. Each overtone matches what Einstein's equations predict. That's extraordinary. Because if even one overtone had not fit, that might have been the first real crack in general relativity. Instead, we see harmony. Beautiful, terrifying harmony. The universe is performing Einstein's equations with the precision of a symphony. But here's the paradox. The more these black holes obey the theory, the more they hint that something else might be hiding beneath. Something waiting to be revealed in the next collision. What we're witnessing isn't just astrophysics. It's theoretical physics in its rawest, most beautiful, most dangerous form. These black holes aren't just crushing stars, they're testing ideas. Let's start with the Kerr solution, a mathematical model of a spinning black hole, published in 1963. It's elegant, precise, and one of general relativity's crown jewels. The signals from GW241011 and GW241110 gave physicists a rare chance to test that solution. How? When a black hole settles after a collision, it rings down like a bell. The frequencies and decays of these rings should match the predictions of Kerr, and they did. So far, the Kerr solution holds, stronger than ever. But the implications go further. Enter ultralight bosons. These are hypothetical particles, lighter than anything we've ever observed. Some theories predict they could interact with black holes, draining their spin energy over time. But here's the twist. The black hole in GW241011 is still spinning extremely fast. That means, if ultralight bosons exist, they can't have the right mass to affect this black hole. Entire ranges of possible masses are now ruled out. This is particle physics, through the sound of space-time. These mergers don't just test Einstein, they test the unseen layers of reality. And there's more. The strange spins, misaligned, reversed, suggest these black holes may be second generation, meaning they're not original black holes formed from stars, but the offspring of earlier collisions. That implies a cosmic ecosystem where black holes form, merge, and form again, not in isolation, but in dense star clusters or chaotic galactic cores. If that's true, then the universe is far more dynamic and violent than we imagined. So from two clean signals we reach into Einstein's geometry, quantum theory's missing pieces, the origin and evolution of cosmic monsters, all because space itself happened to ring. Two signals, two black hole mergers, both matched Einstein's predictions. Both revealed strange, spinning monsters. But neither answered the most important question: what comes next? If these black holes are second generation, then the universe is recycling itself in ways we didn't expect. Dense star clusters may be black hole factories, where mergers happen again and again. And if so, then what happens when a third-generation black hole forms? How fast could it spin? Could it cross the boundary where Einstein's theory starts to fail? And what of the signals we haven't yet caught? As LIGO, Virgo, and Kagra continue their upgraded runs, more sensitive, more precise, they may uncover mergers with even more chaos, tilted spins, wild orbits, unknown physics, and somewhere in that data, we may finally catch the first true break from general relativity, a moment when the wave doesn't quite match, when the bell rings off-key, not a failure of Einstein, but a door opening. Einstein gave us a map of the universe, a framework so elegant it has guided science for over a century. But black holes were never just answers. They were questions, folded in gravity. Now, the universe is speaking in waves, and we are learning how to listen. Maybe the next signal will sound a little off. Maybe the harmony will slip. And in that slip, just maybe, we will hear something new. Not to replace Einstein, but to stand beside him. Because every great theory ends, not with silence, but with the start of another song.